Welcome back, everyone. After these few days where we deviated into other subjects, Friday session being our first discussion on IFRS 17. Today we're starting classification, new chapter. We haven't quite finished the very final sections at the end of chapter 3. I would say we've done a few days away from the book. Probably a good idea to start with something fresh. They're going to be similar ideas to chapter 3. And as I'm sure the introduction is going to remind us, classification is where we are not predicting numerical variables. Our Y is going to be qualitative. And that's what we mean by classification, different classes. It could be two classes. Political party A, political party B. Let's get started. The linear regression model discussed in chapter 3 assumes that the response variable Y is quantitative, but in many situations, the response variable is instead qualitative. For example, eye color is qualitative, taking on values blue, brown, or green. Often, qualitative variables are referred to as categorical. We will use these terms interchangeably. In this chapter, we study approaches for predicting qualitative responses, a process that is known as classification. Predicting a qualitative response for an observation can be referred to as classifying that observation, since it involves assigning the observation to a category or class. Same thing. On the other hand, often the methods used for classification first predict the probability of each of the categories of the qualitative variable as the basis for making the classification. So in this sense, they also behave like regression methods. So as an intermediary step, I'm just going off script for a second, many of the approaches that we shall explore when designing a classification model have at their underlying logic an approach that's still similar to regression, because we're first actually going to predict probabilities. Probabilities are numerical from 0 to 1. It's a continuous numerical variable. And then as a next step, based on those probabilities, you will then actually classify each observation in the relevant buckets or list of possibilities. There are many possible classification techniques or classifiers that one might use to predict a qualitative response. Yeah, and you may remember some of these from chapter 2. We touched on some of these in sections this and that. In this chapter, we discuss 3 of the most widely used classifiers: logistic regression, hopefully I'm pronouncing that correctly, linear discriminant analysis, and k-nearest neighbors. We discuss more computer-intensive methods in later chapters, such as generalized additive models. That's chapter 7. In chapter 8, we will discuss trees, random forests, and boosting. And boosting is one of those things that we have had the opportunity to mention, especially when we had first started out this which is this book. It's something that I have absolutely no idea what it means. I guess it's going to work on these trees and on these random forests, but you see it a lot in these data science competitions. Yes, the same type that Kaggle is very well known for. And chapter 9, support vector machines. 4.1, let's have a look at what classification is all about. Classification problems occur often, perhaps even more so than regression problems. Such examples include a person arrives at the emergency room with a set of symptoms that could possibly be attributed to one of three medical conditions. Which of the three conditions does the individual have? 2, an online banking service must be able to determine whether or not a transaction being performed on the site is fraudulent on the basis of the user's IP address, plus transaction history, and so forth. So already we're starting to list the predictor variables. So in the first point, that would be your set of symptoms. They could be visible symptoms or measured with a thermometer or other device. In the banking example, we have IP address, plus transaction history. And moving to the final example, on the basis of a DNA sequence for a number of patients with and without a given disease, a biologist would like to figure out which DNA mutations are, and this is a new word for me, deleterious, which apparently means disease causing, and which are not. So you're linking what kind of DNA strands, what kind of DNA encoding actually causes a specific disease. Just as in the regression setting, what's really great about this chapter, a lot of it is going to be a revision of chapter 3, when we were working with simple and multiple linear regression. We're a lot more familiar with the notation. Hopefully we've developed better intuition on how to organize just the information and the information flow, right, throughout the just the generic modeling process. And every model really starts from the data, from the training or from the set of training observations. Just as in the regression setting, in the classification setting, we have a set of training observations. And do remember, x1 is, in actual fact, a vector. It could be a vector with a single component, but more often than not, just as we had the multiple regression, if it was the advertising data, that was each xi actually had three components, the relating to the advertising budgets for TV, was it newspaper and radio. So x1, y1 until xn, yn, that we can use to build a classifier. We want our classifier to perform well, not only on the training data, but also on the test observations, right? That were not used to train the classifier. The classifier is the model. It's a model. It could be just your brain, the way your brain perhaps subconsciously classifies people, animals, companies. One way of, or usually the best way of testing your model is if it actually works on data that wasn't in fact used to design the model, to estimate the parameters, those betas that we had in chapter 3. In this chapter, we will illustrate the concept of classification using the simulated default dataset. And this is a good opportunity to see if we can find it in R. Let's run library ISLR, question mark ISLR. Doesn't seem to do anything, or it's still loading. So let's just look for it over here. ISLR, click over here. It's made up of these different, it's just data sets. Other packages might have functions and maybe other items. I can really only think of data sets and functions. And here it is, credit card default data. And it's explaining we can load it. Now if I just do this, I don't think it works. Oh, it does. Okay, so it's a summary of default. What we'll do is if it's numerical data, it will give you sort of the quantiles and the mean. And we widen this, it would appear that we only have 4 variables. One of them shall be our response variable, what you're trying to predict. I can only assume that default is what any bank would try predicting, right? The likelihood of a borrower defaulting, missing on an interest payment, falling behind in what they owe. And I would imagine we're going to try modeling the likelihood of default based on the student status, their balance, and their income. Another great way of looking, sort of getting a first impression of the data is the STR function. And this gives you one line for each variable. Again, default, student, balance, income. Default and student are categorical variables. They are a factor type. Balance and income, that's numerical, isn't it? Let's go back. We are interested in predicting, there we go, whether an individual will default on their credit card payment on the basis of annual income and monthly credit card balance, meaning at least for the time being, we're not going to use the student variable, neither as a response. We're not going to predict if a person is a student or not, which wouldn't be too interesting, would it? Usually the bank has that kind of information. What it doesn't have is whether a borrower is going to default in 6 months' time. The data set is displayed in figure 4.1. Here we go. Please still think of, and I'll just highlight it over here in pink. Please still think of this as a 3-dimensional plot. There are 3 dimensions. There's income and balance. Those are predictor variables, our x1 and x2. Y is the color. Y is the green circles, which I think mean, did I say green? The blue circles, which are the person did not default over the lifetime of the loan. Orange is, well, the person did default. Let's see, can we do this in R? I don't know how, so hopefully it explains it over here. Let's see. We have plotted annual income and monthly credit card balance for a subset of 10,000 individuals. Is that the data that we have? Is it 10,000? Yes. So we have 10,000 observations. They haven't, the authors, the book doesn't plot each one of them, so maybe they've only taken, it doesn't seem to specify, maybe they've only taken 1,000, for instance, for the simple reason that otherwise, for the purposes of the book, you might end up with a plot which is so cluttered, so dense with information that actually loses explanatory power. It'd be interesting to see how one does that in R. The left-hand panel of figure 4.1 displays individuals who defaulted in a given month in orange and those who did not. So, what is the difference between, oh, it's for each one, right? It's for balance and for income. So the natural question to ask is does income have a statistically significant effect on defaulting? Now the closer these medians are, that might suggest, the closer they are, you would intuitively think that maybe income doesn't really help explain or predict whether a person is going to default or not. Let's see if it makes sense. Well, it kind of makes sense, right? What are we expecting? The blues, if you look at their income, so those individuals who did not default, they do have a higher median than those who defaulted. But you know, the box plots are relatively similar. Whereas balance, and what is balance over here? This is not your savings. I think this is how much credit card debt. You can see the explanation in this pane over here. The average balance that the customer has remaining on their credit card after making their monthly payment. So the larger that balance is, actually, let's flip that around. The observations that do default, if you look at their profile, if you summarize them, their balance is it more than double? Their median balance is more than double, and this is exactly what you would expect, right? Now, it doesn't necessarily mean that you can't find situations where it's the other way around, but just when you're first looking at the data, you're kind of hoping that it exhibits so-called common sense characteristics. Those who defaulted were those that, on average, had a larger credit card balance than those who did not default. The overall default rate is about 3%. So we have plotted only a fraction. Why are they saying 3%? That's over here. Do we see it? Yes, default. That's 333. So it's 300 would have been exactly 3% of these 10,000 observations. So it's just over 3%. The overall default rate is about 3%. So we have plotted only a fraction of the individuals who did not default. Otherwise, this would just be blue. You would have 9,700 blues and only 300 greens. Why do I keep on saying green? Orange. It appears that individuals who defaulted tended to have higher credit card balances than those who did not. In the right-hand panel of figure 4.1, two pairs of box plots are shown. The first shows the distribution of balance split by the binary default variable. The second is a similar plot for income. In this chapter, we learn how to build a model to predict default y for any given value of balance x1 and income x2. And as I would imagine, as soon as you learn how to do it for two predictor variables, it is no challenge to extend it to however many predictor variables you would feel a model predicting something else should include. Since y is not quantitative, the simple linear regression model of chapter 3 is not appropriate. We're not going to be we're not going to be fitting lines, planes, or any other linear geometrical object. It is worth noting that figure 4.1 displays a very pronounced relationship between the predictor balance and the response default. What we mean by pronounced is this, what would look like, but we'll have to quantify, but what would look like a significant difference between the median balance of those who didn't default against those who did. In most real applications, the relationship between the predictor and the response will not be nearly so strong. However, for the sake of illustrating the classification procedures discussed in this chapter, we use an example in which the relationship between the predictor and the response is somewhat exaggerated. So this is very clear cut, right? Even if this chapter has hypothesis tests similar to the t-statistic, there clearly is a relationship between, or there is a strong, even just looking at these simple summaries, there's a strong indication that an individual's balance tells you a lot about what you would expect when it comes to those same people paying off their debts. Why not linear regression? We have stated that linear regression is not appropriate in the case of a qualitative response. Why not? Suppose that we are trying to predict the medical condition of a patient in the emergency room on the basis of her symptoms. In the simplified example, there are three possible diagnoses: stroke, drug overdose, and epileptic seizure. We could consider encoding these values as quantitative response variable y, as follows. So there's nothing stopping us from giving them a numerical value. Of course, I imagine what the issue is going to be is, since the model fits a line or a plane or whatever, if for a specific set of symptoms, it gives you an output of 1.5, you can't really interpret 1.5, can you? I mean, even if you had to try saying, okay, it's the average between a stroke and a drug overdose, so it's not probably that useful, is it, to the physicians? Using this coding, least squares could be used to fit a linear regression model to predict y on the basis of a set of predictors x1 to xp. Unfortunately, this coding implies exactly an ordering on the outcomes, putting drug overdose in between stroke and epileptic seizure and insisting that the difference between stroke and drug overdose is the same as the difference between drug overdose and epileptic seizure. In practice, there is no particular reason that this needs to be the case. For instance, one could choose an equally reasonable coding where they've just reordered these three classes, which would imply a totally different relationship among the three conditions. Each of these codings would produce fundamentally different linear models that would ultimately lead to different sets of predictions on test observations. If the response variables values did take on a natural ordering, such as mild, moderate, and severe, and we felt the gap between mild and moderate was similar to that between moderate and severe, then a 1, 2, 3 coding would be reasonable. Unfortunately, in general, there is no natural way of converting a qualitative response variable with more than 2 levels into a quantitative response that is ready for linear regression. So we're speaking of more than 2 levels. Now, if it is 2 levels, so for a binary qualitative response, the situation is actually better. For instance, perhaps there are only 2 possibilities for the patient's medical condition. I mean, you can imagine that everything else has been ruled out. So maybe you've applied one test that checks everything, with the exception of stroke and drug overdose. So now you're down to seeing which of these two the specific patient is actually suffering. We could then potentially use the dummy variable approach. I think this was our last session where we were doing this book, from section 3.3.1 to code the response as follows. Y is equal to 0 if stroke, Y is equal to 1 if drug overdose, and then we could fit a linear regression to this binary response and predict drug overdose if our predicted Y is greater than 0.5. And we can already start looking at that as kind of like a probability, right? And stroke otherwise. So if it's greater than 0.5, so it will be rounded to the nearest integer as a 1. Otherwise, it's rounded down to a 0. In the binary case, it is not hard to show that even if we flip the above coding, linear regression will produce the same final predictions. For a binary response with a 0-1 coding as above, regression by least squares does make sense. It can be shown that x beta hat, the x beta hat, obtained using linear regression. So let's stop for a second. X beta hat. Why doesn't this have an index? Why isn't it beta hat 1 or beta hat 2? Well, the thing is, and I'm trying to remember from what we did last time, this would look like linear, this would look like simple linear regression. Is that correct? No, I doubt it. No. This this X can still be a vector. Yeah, like it's a set of symptoms. So this could be a vector. So I don't really like the notation they're using over here, assuming I'm not misreading it. But what you should really think of this is as a summation. X1 times beta 1 hat plus X2 times beta 2 hat, etc., etc. So it can be shown that the X beta hat obtained using linear regression is in fact an estimate, and we're back to probabilities, of the probability that it is a drug overdose given X. What is X? X is just the predictor variables. So in this case, the symptoms. You ask patients or you ask your junior doctors to fill a form for each patient. Or I don't know, it's a questionnaire with 20. Each question measures a symptom. Some of them will be qualitative. So for example, sweating, not sweating. Others will be numerical, temperature, for instance. In this special case. However, if we use linear regression, some of our estimates might be outside the 0-1 interval. Interesting. So, right. Let's have a look. So we are regressing. We're taking the fault as either 0 or 1. That's the coding. If it's 0, I don't know, the person has not defaulted, perhaps. If it's 1, the person has defaulted, which I think is correct, because you get your data points. So for example, 1,500, comma, has defaulted. 2,000 has defaulted. 500 has not defaulted. 2,000 has not defaulted. If you then try fitting, I wonder if we can do it in R. When you then try fitting it in using linear regression, using the LM function, you have your least squares method, you're minimizing the residual sum of squares, the RSS, and you estimate your slope parameter, your beta 1 hat, and your intercept parameter, your beta 0 hat. Now, what happens is that for certain inputs of balance, we get probabilities that are outside the 0-1 interval, which we need for probabilities. No, not only that, but if I extend the line, not only will the line give us negative probabilities, but if you extend it far enough, say like this, we may now have, if it's long enough, yeah. So for balances over here, we now have probabilities that are greater than 1. Again, something that you would want to avoid. Making them hard to interpret as probabilities. Nevertheless, the predictions provide an ordering and can be interpreted as crude probability estimates. Curiously, let's see, it turns out that the classification that we get if we use linear regression to predict a binary response, will be the same as the linear discriminant analysis procedure that we discussed in section 4.4. But before 4.4, we're going to do logistic regression. However, the dummy variable approach cannot be easily extended to accommodate qualitative responses with more than 2 levels. For these reasons, it is preferable to use a classification method. So that's it. Probably this is going to be the last time that we mention regression onto classification methods that are truly suited for qualitative response values such as the ones predicted next. Just have a look at my phone. Just send you a reply to that message that you sent me earlier. And we have like 20 minutes to go. Logistic regression. Consider again the default dataset where the response default falls into one of 2 categories, yes or no. Rather than modeling this response Y directly, logistic regression models the probability that Y belongs to a particular category. And this probability, and this is from where we get the name logistic, is going to follow this so-called logistic curve. For the default data, logistic regression models, let's read that again. For the default data, logistic regression models the probability of default. For example, the probability of default given balance can be written as probability default equals yes given a specific balance. So that balance might be 500, it might be 1,000. The values of probability default equals yes given the balance, which we abbreviate to p-balance, will range between 0 and 1. Then, for any given value of balance, a prediction can be made for default. For example, one might predict default equals yes for any individual for whom p-balance is greater than 0.5. Alternatively, if a company wishes to be conservative in predicting individuals who are at risk for default, so this is a bit subjective, although there are going to be ways of kind of getting this cutoff. So 0.5, the book's then mentioning 0.1, getting a cutoff that's based on a specific set of instructions. Okay, the logistic model. How should we model the relationship between P of X and X? For convenience, we are using the 0-1 coding for the response. In section 4.2, we talked of using a linear regression model to represent these probabilities. P of X is equal to beta naught plus beta 1 X. If we use this approach to predict default equals yes using balance, then we obtain the model shown in the left-hand panel of figure 4.2. So now we're looking at this chart over here. Let's read that again. If we use this approach to predict default equals yes using balance, then we obtain the model. So at this stage in the book, we haven't yet described how to create this model. However, what it's telling you is once you do have something like this, that until a balance of, for instance, 2000, let's take maybe 1500, the probability of defaulting is around 10%. That's what the model would then tell you. There's always a risk, right? You could have someone defaulting on a balance, I mean, at least theoretically, of $1 or even less. Here we see the problem with this approach. Oh, in fact, this paragraph, we're still discussing this chart over here. It's on the left, right? And we're going to discuss negative probabilities, which is why instead we use the logistic model. Yeah, in fact, I missed that. The book is clearly speaking of linear regression, and I'm already thinking of modeling logistically. Here we see the problem with this approach. For balances close to zero, we predict a negative probability of default. If we were to predict for very large balances, we would get values larger than 1. And you want to avoid both situations. These predictions are not sensible since, of course, the true probability of default, regardless of credit card balance, must always fall between 0 and 1. This problem is not unique to the credit default data. Anytime a straight line is fit to a binary response that is coded as 0 or 1, in principle, we can always predict probability of x is less than 0 for some values of x, and probabilities of x is greater than 1 for others, unless the range of x is limited. The range, in the sense, the interval of x is limited. So instead of working on the entirety of the x-axis, if it's simple linear regression, then you'd only be working over specific intervals. So for instance, from 0 to $50,000 if it's balanced. And again, even so, even if it's on a limited, if it's on a specific interval, you may still have probabilities less than 0 or greater than 1. To avoid this problem, we must model P of x using a function that gives outputs between 0 and 1 for all values of x. Many functions meet this description. In logistic regression, we use the logistic function. P of x is equal to, so notice it's quite similar to linear regression. You have this over here, and again, x is this is simple. We're looking at only one predictor variable. X is the balance, and then we'll extend this to, for example, allow for the, for the income as well. And then you'd have multiple terms with x. to fit this model, we use a method called maximum likelihood. It's extremely important in many parts of statistics. You'll see it abbreviated as MLE, maximum likelihood estimate or estimator, which we discuss in the next section. Now we're coming to the right-hand panel. The right-hand panel of figure 4.2 illustrates the fit of the logistic regression model to the default data. Notice that for low balances, we now predict the probability of default as close to, but never below 0. Likewise, for high balances, we predict the default probability close to, but never above 1. The logistic function will always produce an S-shaped curve of this form. And so, regardless of the value of x, we will obtain a sensible prediction. We also see that the logistic model is better able to capture the range of probabilities than is the linear regression model in the left-hand plot. The average fitted probability in both cases is that 3%, which is the same as the overall proportion of defaulters in the data set. After a bit of manipulation of 4.2, we find this. So if you take this equation, should I call it an equation? It's more like an identity, right? It's for every value of x. You're not going to solve this, are you? You could make this subject of a formula. It's not too difficult. If you make it subject, you cross multiply. On one side, you have only terms that contain this e to the term. Take it out as a common factor. If you take it out as a common factor and take out what you're left with as a denominator, we find this. This is also an identity. Now, the quantity p of x divided by 1 minus p of x is called the odds. So this is the probability of x happening, this is the probability of x not happening. So to think of odds like on horses or political candidates. You see, for example, the 7-2 odds. And can take on any value between 0 and infinity. Yeah, 0 is if the numerator is 0. Infinity is if the numerator is 1. You would end up dividing by 0. Values of the odds close to 0 and infinity indicate very low and very high probabilities of default, respectively. For example, on average, 1 in 5 people. So what 1 in 5 people, the odds, this is not a fraction. You think of this as 1 in 4 means 1 yes, 4 no, out of a total of 5 will default. Since p of x is 0.2, implies an odds So what are we saying? I think we're saying take 5 people and they have an odds of 1/4 that they will default. In that case, 20% of them are expected to default. Because if you do in fact take 20 over 80, 20% over 80%, you will get 1/4. Likewise, on average, 9 out of every 10 people with an odds of 9 will default. So an odds of 9 is 9 on 1, right? 9 on 1. But this 9 on 1 means if it's an odds of 9 on 1, it is 9 out of 9 plus 1. Odds are traditionally used instead of probabilities in horse racing, since they relate more naturally to the correct betting strategy. So, although we often use chance, probability, odds interchangeably, in this context, although they are related to each other, they don't mean quite the same thing. So if the probability is 1 in 5, if the probability is 20%, the odds are 1. Might be a way of reading this. If I quickly just type how to read odds on my phone. How to read odds. Okay, so you have 7 to 2, for instance. Let's start with the second example, which is what I'm going to highlight in orange. Likewise, 9 out of every 10 people. So probability of 0.9 is the same as odds of 9 to 1. Okay. So we're going to continue manipulating this identity by taking the logarithm of both sides of 4.3. We arrive to this, and now this is called the log it, or the log odds. We see that the logistic regression model 4.2 has a log it that is linear in X. So logistic regression has a log it, this, that is linear in X. Recall from chapter 3 that in a linear regression model, beta 1 gives the average change in Y associated with a 1 unit increase in X. In contrast, in a logistic regression model, increasing X by 1 unit changes the log odds by beta 1. The log odds by beta 1. Not the odds. So the odds are not going to be linear. But this, how does this change? If you increase this by 1, the orange will increase by beta 1. Which means that it multiplies the odds, the actual odds now. The actual odds by e to the beta 1. So it increases the log odds by by beta 1. Yeah, and then if you do e to the on both sides to remove the log, the odds increase by e to the beta 1. However, because the relationship between p of x and x in 4.2 is not a straight line, beta 1 does not correspond to the change in probability of x associated with a 1 unit increase in x. The amount that px changes due to a 1 unit change in x will depend on the current value of x. So it depends on the current value of x. But regardless of the value of x, if beta 1 is positive, then increasing x will be associated with increasing p of x. And if beta 1 is negative, then increasing x will be associated with decreasing p of x. So we still keep the direct or inverse proportion relationship. So the sign of beta 1 does tell you whether you should expect the response variable y to increase or decrease. The fact that there is not a straight line relationship between probability of x and the fact that the rate of change in p of x per unit change in x depends on the current value of x can be seen by inspection of the right-hand panel of 4.2. So clearly it's not a linear relationship. So the probability of default does increase as the balance increases, but it depends on where you are. So if your balance is 1,000 and it increases by 10, there isn't going to be that much of a change in your probability of default. Whereas over here, it's a lot more sensitive. The probability is a lot more responsive to changes in the balance. But this is probably a good time to end this. Okay, thanks. We'll continue tomorrow.